So, if you haven't been here, we last class did the gravity lab. And this was what we were trying to figure out. We wanted to know what is the relationship between mass of an object and the force gravity exerts on it. And we were pretty certain that there was a relationship because it only makes sense, at least I would think, that the more massive something is, the more force gravity would pull on that object with. So we took some data, collected some data, and we found out this was our result. Everybody in class measured 7 or 8 different objects, got masses for each of those objects, got the force of gravity on each of those objects, converted the masses from grams to kilograms, put those in the data table along with the force of gravity, and this is the graph that we got, which looks very linear. Like we have a very linear graph here. That line is very straight. For the data, probably of any of the data that's been collected in here, this is probably the most linear that we've had in terms of the points are not very far away from the best fit. So that's a good sign. That means that this relationship is a certain kind of relationship, but that we must have collected decent data to get data that's this close to a perfectly straight line, which led us to this. So I had everybody sketch this in their comp books. And again, it is linear, which means straight line. And so that led us to the question, so what kind of relationship is that? Yes, we would call this a linear graph because it's a straight line, but what kind of relationship is that? Which I don't know if you remember because we had talked about this several times in the past, but I'm assuming that you probably have forgotten that there is a 2-word relationship that this is showing. It's 2 words. I don't know if you remember. I'll scroll down here. It's telling us that the force of gravity is directly proportional to the mass of an object. So obviously, because the line goes up, because it has a positive, well, it doesn't have to have positive, because it has a slope at all, that means there is a relationship. If it was horizontal, if the line was horizontal on the graph, that would mean that the gravity force is not changing at all as mass gets bigger. And that's not the case. We see that the gravity force is affected by how much mass an object has. And so not only is it affected by it, it is affected in a directly proportional relationship. And remember, another word for proportion is ratio. That means we have a consistent ratio of force of gravity for every unit of mass. Now, I asked each group to write out the equation of their line, which when you look at graphical analysis, we have some information in the box here. We have an m for the slope. We have a b for the y-intercept. So we have the m and the b. The y and the x are what? Well, force of gravity and mass. So we have a y and an x variable, but then we also have an m and a b. So you're supposed to then be able to write out the equation for the line based on this graph from graphical analysis. Now, what people weren't quite sure about then is what unit of measure would be on the slope. Because remember, and some of you continue to forget this, there has to be a unit of measure on anything that's a number. Numbers are measurements of something. And so we need to know what the unit of measure is on both the slope and the y-intercept. Well, remember, for this graph, and we didn't have to do it because graphical analysis did it for us. You didn't have to manually, by hand, go calculate and find the slope. It did it for us. But if you had, you would have had a setup like this. You would have found 2 points on the line that would have hit, hopefully hit grid intersections that would be easy to read. And you would have found that that is a Newton value. So the rise of the graph is force of gravity, and the rise is measured in newtons. The run of the graph is a mass, which is measured in kilograms. So we would have found that you would have taken a rise over a run, which would have been a value in newtons divided by a value in kilograms. And what happens to the units of measure? They stay there. Just like in the previous couple units, we had centimeters on top, seconds in the bottom. So it stayed there. It was centimeters per or for every second. Or we had meters for every second. Or we had miles for every hour. So the units of measure that are on our rise and our run stay with the numbers, and they form a fraction. Okay. So when we look at the next slide with all of our equations and stuff on it, and again, this isn't your class necessarily, this is just a slide here. I wrote mine down. I wrote that first. I did this and I had a slope of almost 10, 9.87. And again, it's newtons / kilograms because that's the unit of measure of the rise over the run, the newtons for every kilogram. So again, my y variable is force of gravity. My x variable is mass. My slope I found in my box. My y-intercept was the b in my box. And notice it has a unit of measure of newton. The y-intercept is on the y-axis. So that is a measure of newtons. So that's mine. Oh boy, let's see. Let's get this up here. Now, let me get this a little smaller, I guess. Let's see. Oh, come on. Oh my gosh. There we go. So we found out, oh, look, it says right there, force of gravity is directly proportional to the object's mass. So there we go. We know it is a directly proportional relationship because we have a constant slope. And the slope, the rise over the run, is a ratio. It is a proportion. So what exactly is the proportion? Well, remember, we have in the past, we've written our slopes out in sentence form, which is what we did here. This says that there are 9.83 newtons of gravity force for every, again, that's what the slash means. If we don't have the unit of measure on the slope, then the slope doesn't tell us what it means. The units of measure on it, the number, the slope, tell us what that value means. And it means that there are 9.83 newtons of force of gravity for every 1 kilogram of mass. It's a 9.8 something to 1. Or if you look at everybody's numbers, again, they're very similar and they're all really close to 10. So let's just call it 10. It's just an easier number to deal with. So it looks like this gravity thing, excuse me, it looks like this gravity thing is a 10 to 1 ratio, 10 newtons to 1 kilogram ratio. So every kilogram that an object has of mass, gravity pulls on that 1 kilogram, every kilogram, with 10 newtons of force. So if you're 2 kilograms, then you've got 20 newtons of gravity force. 3 kilograms, you got 30. 4 kilograms, you got 40. 5 kilograms, you got 50 newtons of gravity force. So again, for every 1 kilogram, it's another 10 newtons-ish, 10-ish newtons of gravity force. I hope that makes sense. That's what the slope's telling us. The next question was, what is the y-intercept telling us? This one, again, I had you write down a statement way back. And I've tried to have you use that statement to tell us what the y-intercept means. The y-intercept is the value of the y variable when the x variable is 0. Think about it. If we don't have a mass, if we have 0 mass, what's 0 times 9.83? Or 0 times 9.88? Or 0 times 9.82? Or 0 times 9.87? Or 0 times 9.58? You get the point. It's 0. Those are gone. This whole thing is gone. And what's left? This. So it's telling us that the force of gravity, when you don't have any mass, in this case for this group, was negative 0.11 newtons. Negative 0.11 newtons. That seems odd. This group, if that group put something on the hook of the scale that has no mass, the scale would still read negative 0.24 newtons. What does that mean? What could that mean? Should we have a value? Should the scale read anything when there's nothing on the hook? I'd say no. So what should our y-intercepts be? I would say 0. They should be 0. They're not. I even had 0.04. Mine's positive. This group had negative 0.04 newtons. So what does this mean? Well, if you had a negative one, that means not only is the scale reading something, it's reading negatively. So gravity isn't even pulling down. So if you don't have any mass, gravity's not pulling down, it's actually pushing you up. That seems strange. That really seems strange. So that's even more odd than the scale reading something. So what could possibly explain the fact that your scale was reading something, or so your equation says? Your equation says that your scale would read something even with nothing on the hook. I suppose it's possible that you misread the scale and your measurements are just off. That could be an option. Or the scale itself was not reading 0 when you started. Maybe your scale was off a fraction of a newton. And the little plunger thing that goes up and down as you hang stuff on the scale, maybe it wasn't actually at the 0 line, and you should have maybe adjusted that to make sure that that was exactly perfectly at the 0 line. That's an option too, I suppose. When I would go back over there after a class was done collecting data, and I would look at a couple of the scales, it didn't look like they were zeroed. It didn't look like the plunger, the edge of the line that you were reading from, it didn't look like it was actually at the 0 on the scale. So that could have been a problem. But they should be 0. I would think that it makes sense that if you don't have mass, you don't have gravity pulling on you. So we'll just leave it at that. Now, what else was there? Oh, yeah. So we then started talking about, well, what does this gravity force thing mean? Oh, that's not it. Oh, I don't remember which slide it was. Was it this one? Oh, that's the one we were already on. So, oh, where is this other slide I have? Oh, it's, oh no. Is this the one? No. Uh-oh, I can't find my slide. Is this it? No, we already did that. Is this it? No, we already did that. Oh no. I can't find my slide. Uh-oh. Is that it? Oh, this is it. Yes. Oh, I must have put some stuff on the wrong slide. Maybe not. I don't remember. Anyway, so general equation and big idea. Here's what we found, okay? It looks like if we were to just put kind of for everyone, and this would be notes you should probably write down. From the lab, what we found out was there's about 10 newtons of gravity force for every kilogram of mass something has. Which means if you want to know what the force of gravity is on something, well, it's 10 times how much mass the thing has. 10 times the mass is the force of gravity. Now, this 10 newtons for every kilogram, A 10-to-1 ratio, again, we were talking about directly proportional. That's the proportion. It is a 10-to-1 proportion. That is what we call gravitational field strength. That is gravitational field strength. And for objects around the surface of the Earth, it's 10 newtons per kilogram. That's how strong Earth's gravity is. It pulls with 10 newtons of force on every kilogram an object has. This then is how we normally would write that. We would say that the force of gravity on something is mg. What's g? That's g, little g. It is the symbol we use for Earth's gravitational field strength. So mg is the force of gravity, m times g. Okay. Now, I had heard people use the word weight as you were collecting data. I heard people saying, we have to weigh this. How much does that weigh? Weight. So, are you telling me that weight is what the force of gravity is? It sounds like that's what people were saying. People in class agreed that's what they meant, that the weight of an object is the force that gravity pulls with. I agree. That actually is what we call weight. So the mass of an object times the gravity strength is what we call weight. Now, we have to differentiate here, people. Mass is how much matter or how much stuff. Remember, we said that mass was the measure of how many particles something's made up of. So, how much matter there is, how much stuff an object is made of, is mass. That is not the same thing as weight. Most people use them as synonymous. They are not synonyms. They are not the same thing. Weight is gravity's force on that matter. So mass is how much matter there is. Weight is how much gravity pulls on that, with how much force gravity pulls, which is, again, 10 newtons for every kilogram if you're near the surface of the Earth. Now, another thing I did in class, I said, hey, if you weigh 165 pounds, because, see, we don't talk about mass in the English system. Everything's just pounds and ounces, which is weight. That's weight. That's a force. Pounds is a force. And so whenever we talk about how much something weighs, we're talking about pounds and ounces. That's not how much stuff something's made of. That's how much it weighs. So if I weigh 165 pounds, there's actually each kilogram here on the Earth weighs about 2.2 pounds, which puts me at about 75 kilos. I have a mass, I am made up of 75 kilograms. So if you were to compare me to one of these things, like this is a kilogram. This is 1,000 grams. I don't know if you can see that. It says 1,000 grams on there. This is 1,000 grams. I am 75 of these if we had them all stacked up. That's how massive I am. 75 of these. Well, then how much do I weigh? Well, we said 165 pounds. Well, yeah, but what is that in newtons? Well, you take my mass of 75 kilograms times the gravitational field strength, how strong gravity is on the Earth, which is 10 newtons for every kilogram, and I am 750 newtons. Well, I thought you said I was 165 pounds. Yes, those are the same things. 165 pounds is 750 newtons. That means a newton is a very small unit of force. If 165 pounds is 750 newtons, then a newton's not much. It's only a few ounces. So that's how those compare. Okay, so you need to make sure you understand the difference between mass and weight. They're not the same thing. And that's why earlier in the year, when you were you were measuring masses, and we were talking about mass versus volume and density and those things. A lot of people kept saying weight. It's not weight. You were not weighing those things. You were massing them. You were determining their mass, measuring their mass. which is not the same as weight. I hope you see that. The last thing we did today is I gave one more example of a force scenario here. So I have a young fella here. I guess it could be a young lady as well with a blue mohawk, pushing a desk along a floor. Notice the markings on here indicate that this person is pushing with what? I'd say the desk is moving with it seems like a constant velocity. You should pause the video, sketch this, write out a motion map, and sketch a force diagram with all the forces named appropriately. This is the last example we did before we took the quiz. Pause the video, do that, then come back. Hopefully, after you've come back now, you sketched a force or a motion map that looks like this. If the desk is moving at a constant velocity, then you should show constant velocity, which means our A is 0. We don't have an acceleration because it's constant velocity, which means then our forces have to be what? Our forces have to be not unbalanced, but balanced, which means our force diagram should look something like this. We have a force of gravity on desk. We have a force of floor up on desk, and those are balanced. We have a force of person. Notice I'm using subscripts now. I'm using less words. I'm not even writing the whole word force out. I'm just using capital F, and then I'm writing a subscript G for gravity force, subscript floor for the force of the floor on desk, subscript person for the force of person on desk. So I'm trying to eliminate so many words. Because the person is pushing, we know there has to be a force of person on desk. But is there a force of friction on the desk? If the forces have to be balanced, then do you have any other idea of a force that could be acting opposite of the force of the person on the desk? Any other idea other than friction? I can't think of one. There's nothing else in the picture. We literally have a floor with a desk, and we have a person pushing the desk. There's no other objects. So the only other force that would make any sense is if there is a force of friction acting on the desk, opposing the motion of the desk, balancing out the force of the person. So we have balance horizontally, we have balance vertically, everything is balanced. That's what you will have to do for the quiz. Okay? So hopefully that helped. Sorry that this took so long, but hope you're doing well if you're not here. And if you even watch it, I'm sure you won't even watch it, but whatever. Hey, it's there for anyone to look at if they need to go back and refresh their memory. So, talk to you later.